last time we started chapter 4, and in the short lecture we studied the superimposable test, so which is basically used to see whether two objects are the same, and also we learned about the internal plane of symmetry, and we can use that as a criteria to determine whether an object is chiral or not, right? And then we learned the concept of stereocenters. Basically, it's a carbon or atom that is connected to four different substituents. And we also learned the concept of enantiomer and their properties and physical and chemical. And particularly important is the optical activity, which different enantiomers have opposite optical activities. And the two types of interaction, one is chiral-chiral, one is chiral-achiral. All right, so just two small things to keep in mind. So the nomenclature drill is open, and also for a very small number of you who haven't signed up for the tutorial group, please do so. Okay, so at the end of the last lecture, we have learned some of the CIP rule, so which I will go over very quickly with you today. So the first is that you assign priorities based on the atomic number, right? In this case, iodide is the biggest and the hydrogen the smallest. All right, and then you put the smallest functional group or the substituents in the back to the back, and you look through this direction. Okay, then what you see is the three bigger substituents facing up to you. All right, and so once you have these three groups facing up to you, then you use your left or the right hand to see whether it matches the rotation direction of your hands. Okay, so if you point your thumb to the back of the smallest to the back, then if it meets your left hand, then it's S. Okay, it's also counterclockwise, and if it meets the rotation of the right hand, we can say it's clockwise and it's R. All right, and another way to represent this is that you look at this way, put the smallest group on the back, then if it's 1, 2, 3 clockwise, then it's R. If 1, 2, 3 is counterclockwise, then it's S. All right, so that's very easy, the basic rules for the CIP convention, and this is really the foundation of all the stereochemistry we're going to learn through the rest of the semester. Okay, and then there are more complicated extension of rules for the CIP convention. All right, so we say that if the atomic number of the different substituents, we compare them, then the biggest one has the highest priority, right? So, but what if we have two substituents, both have the substituents with the same atomic number? For example, this one. So we have a CH3 methyl group, and another one is acyl group, right? So the directly connected atom is carbon, the same for the carbon. So how do we compare them? So the thing we do here is that we make sure we know every substituent of the atom we are referring to. Okay, the carbon has 3 H here, right? So we put it down carbon with 3 H. For example, for the acyl, we have a carbon, and that is connected to a carbon. So it has 3 substituents, carbon H, H. So these 2 H's, right? So we compare them one by one, start from biggest. So the biggest one of the HHH is H, right? The biggest one of the CHH is C. So C is bigger than H. So the priority of acyl is bigger than methyl. Okay, and for this one is hydroxy group. The other one is methoxy group. So which is an ether type functional group. Okay, the O has 1 H on it, but for the ether, the O has 1 carbon on it. Okay, carbon bigger than H. So methoxy group on the right has higher priority than the hydroxy group. So for this one, which has this is acyl, right? So carbon HH. For this one, it has the isopropyl, which means the carbon is substituted by 2 methyl group. So you put it on carbon, carbon H. So the first one, biggest one, carbon, carbon, the same. But the next one, carbon. For this one, only H. So isopropyl is bigger. So for the last one listed here, So the carbon has a nitrogen, nitrogen, carbon, and H. Nitrogen is the biggest. And this carbon has a chloride 2H. Okay, but we compare the biggest. The nitrogen is lower than chloride because the chloride is 35 or something. And so the chloride is bigger than nitrogen. So this group has the higher priority. Okay, so that's the first one of this comparison using extension. And a second one of the rule is that what if there are some unsaturation or double bond, triple bond in the substituents you are going to compare, right? So for example, this one, you have carbon, oxygen. So as we previously learned, so the carbon is substituted by OHH, right? OHH. But how do we count this one? It has only have two substituents. So the rule is that if this bond is a double bond, so if a carbon is connected to oxygen as a double bond, then this double bond O is counted as 2O. All right. So if you have a ketone or aldehyde like this, you count it as this is it's equals to this kind of carbon OOH. So if you have an oxygen double bond, then 2 oxygen. All right. So this one should be carbon OOH. So compared with the original one, the carbon OOH is apparently higher, right? Higher priority. So now, what if you have a triple bond? So we already say this isopropyl group have 2 carbon, right? Oh, this is typo. I need to correct this. So these isopropyl group have 2 carbon. So the original carbon should be connected to carbon H, right? So change this. So the original one has a carbon H. But how about the triple bond? So if it's triple bond, you count it as 3. So the carbon is linked to 1 carbon triple bond. It means you can see it as a carbon linked to 3 carbons. All right. So the order of this carbon is carbon. So which is higher than CCH, right? So the triple bond is a higher priority than this isopropyl. So these are 2 very important rules. And so I'm going to show you with some examples, and I will assign it with these rules so you can better understand how these CIP rule and the extension of CIP rules works. Okay, and I'm going to do it with all of you. You may also take out a pen and let's do this together. All right. Screen. So what do we have here? So we have a carbon substituted by an H, bromide, an acyl group, and a methyl group, right? So if we compare the atomic number first, so which is the lowest? Definitely the H, right? Because the H is the atomic number is 1. So we can put a D here. And if you prefer, you can put 4 because the 4 is also the lowest. Okay. Then what's the biggest? The biggest should be bromide, right? Because bromide is like 30-ish atoms. Okay. And it should be much bigger than carbon. So we put which is A, and which is the number 1 substituents. Okay, then acyl methyl is a little bit tricky, right? Because for acyl you have C with 3H. So we have a C with H, H, H. So for acyl, CH2, CH3. So for this carbon, what do we have? We have the biggest is C, H, H. So that means acyl is the priority is bigger than the methyl because the carbon is bigger than H, right? So bromide is the biggest, then the acyl should be the second, right? Which is B, 2. And methyl is the third, which is C, 3. Okay, then which direction should you look at to assign the order of these substituents or assign the CIP rule and the specification of this chiral molecule? You should put the H on the back. Then you look at this direction with your eyes here. Okay. Then what if you look at this direction? What you see is that you have a bromide. Let's see if we put it in the bottom, which is A1. And then the bromide, and on the left is the methyl group. Which is C3. And the other one is acyl, which is B. Okay, then you see whether you can use the what's the wheel, what's the turning wheel. So you put your thumb towards the paper and then see it meet your left rotation or the right rotation. So now it's ABC. ABC. Okay, this direction, this direction. So it should be R, right? Yeah. Oh, it should be S. Sorry. Sorry, it should be S. So the ABC meets your left hand sinister, so it's S. Okay, so the stereocenter is defined as S. Let me check if it's right. ABC. Yeah, it's S. So if we look at the next example, it's a little bit more complicated. Okay, we have more atoms here. So it's the same rule, right? So the smallest one should be the H because the H has the lowest atomic number. So we put D for here. And then we have substituents here. That's N. So it's nitrogen, this one is carbon, this one's a carbon. And the nitrogen should be the biggest because the nitrogen is bigger than carbon, right? So we put the nitrogen is the biggest one, which is A1. And then these two carbon are a little bit complicated, so let's write this way. So we have CH2OH. So this carbon is substituted with the 1 O and the 2 H. So OHH. Okay. The other one is has a double bond now. So COOH. So this carbon should be considered as 2O, right? 2O, and so this one counted as 2O, this one counted 1O, so 3O. That means the carboxylic acid should be a higher order substituents here, right? So it's lower than the nitrogen, but it's next highest. So carboxylic acid, which is B. Then this CH2OH, which should be C. All right. Then now the direction you look at, you put this H in the back, right? The direction you should look at is here. Right? That's your eyes. Okay. And then what you see is that the NH2 is on the left. And then CO2OH on the, NH2 on the right, CH2OH on the left, and the COOH is in the bottom. Then COOH, the NH2 is the biggest, A. COOH is second biggest. CO2OH is third biggest. Then take several seconds, see whether this is R or S. Yeah, just take out your hands and see whether it's the left turn that matches your left hand or the right hand, right? Put your thumb on the paper, pointing down, okay? So A, B, C, all right? That's R, right? So let me check it one more time. Yeah, it's R, okay? So this is the assignment is R. And the direction of the rotation is A to B, B to C. Okay, so let me be honest with you. So this, so on the midterm or the final exam, if you are asked to assign the specification of these chiral centers, so these two will be the easiest level. All right. So what's most likely you will encounter during the exam is that we will put different forms of presentation method of the molecule. For example, if we can put out like the 6-membrane chair conformation, all right, and then we can put this simple one. perspective drawing, and we can have these ring structures, and we can even put the visual projections on the exam, and for a lot of sugars or amino acid, then and also human projections. Okay, so this is some kind of a comprehensive testing of your knowledge, whether you are really mastering your knowledge here. All right, so you can like transform these kind of projections to the way you want, and to see if we can assign a specification for these data centers. Okay, so these all molecules are just for you to practice after the class, but I can briefly talk about several of them. Okay, so for example, for this chair conformation, it's really easy to assign, right? Because you can, if you are really familiar with the chair conformation, you know how it looks like. So you can, in your mind, you can make up these hydrogens here, right? And then you can see, oh, for this carbon, it has a bromine biggest, hydrogen lowest. Then you just need to compare this one and this one, okay? And so for the perspective drawings here, perspective drawing, this is also very easy, right? You just need to, in your mind, that makes up a hydrogen here. Because we didn't draw it here. Oh, okay, then you know the chiral centers, you know the stereo centers, and you can make that assignment. Okay, so for this one, it's a ring structures. You have the OH, and then always make up the hydrogen first, because it's not drawn. Now you know, if there is hydrogen, the hydrogen always the lowest, all right? And then you can make assignment. Because the hydrogen now is pointing back, OH is pointing up, and the OH is the biggest, and this is a CH2, this is a CHC, because it has substitution here, right? So biggest, next, third. So this one should be R, right? And then you don't, then another trick is that if you have a molecule on your exam that is looks like these two, okay? So let's ask you, let me ask you a question. So if you know all the stereo centers here, do you have to redo all the CIP rules to know the stereo center specification here? No, right? Why? Because they are mirror image. If you see, right? If you draw a mirror in between of them, so you can see this OH pointing up, this methyl here, and then all others are fine membrane. So what's the mirror image of our stereo centers? It's S, right? So you don't even need to apply the CIP rules here. You just, if you apply once, then you have a mirror image. You just assume that, you just know that the other is the opposite. So let's see, yeah. So the correct answer is R. This part is R, so this part is S. It's mirror image should be R, okay. And then, so for these several, like the facial projection and human projection, they are the most difficult one, and because you have to convert it, all right? And for example, for this one, just convert it to the way you want it to look like. For example, the way I do this is that you see the H and the chloride are pointing up, right? So I usually just make them pointing up. Okay, then let's see, you look through this direction. Then you have the chloride H like pointing to you. Then you have the chloride pointing back, and then so these the left should be the COO, the ester. The right should be CH2CH3. See, if you convert this facial projection to those kind of like perspective drawing, it's much easier for you to assign the specification of the stereo center. Okay, so the same with these human projections. Okay, just try to be familiar with these different kinds of representation method, human projection, facial projection. Then when you encounter a molecule in exam or in real life, then you can transform it to the way you want it to look like. Okay, without the loss of any chiral information or stereo center information. Okay, so that's so much for the practice, and we should move on with the lecture. So this one we're done. Okay, don't forget to practice on these molecules. Okay, so Then after we learned that there are there is CIP rules that we can, based on the structures of different molecules, assign a specification. And now we know that now we want you to realize that the sign of optical rotation, which is connected to the physical properties of these enantiomers, has no correspondence to the ROS configuration whatsoever. Okay, so you can see that although this has a different so this plus minus is based on the observed optical rotations, the plus or minus here, right? But all these have different ROS. So you can at home if you go home, you can see whether so I think we already did. So let's see. Yeah, that's it, part of the exercise. So this one is S. Okay, so you can see it's connected to the it's not connected to the minus. All right, so you can see you can go home and find out what's the RS here, RS here, RS here, and see whether these RS is related with this plus or minus. The answer is that it's not related. Okay, there is no correspondence between RS and plus minus. Okay, and so after we figure out how to give a specification to the CIP rules of one single stereocenters, okay, let's move on to a more complex system. For example, how about compounds with two stereocenters? Okay, then if I put a compound with two stereocenters on the exam using Fisher projections like these two, okay, you should be able to assign each stereocenters an R or S. Okay, so I did a job for you here. So for this one, the 2 position is R, 3 is R. So it's mirror image, which is 2S, 3S. Okay, because R and S are mirror image. So they are called enantiomer, right? And then we have another pair of enantiomers. So 2R, 3S. Its enantiomer should be 2S, 3R. They're totally reverted. Okay, so they are enantiomers. So the question is, so what's the relationship between 2S, 3S, 2R, 3S? Okay, so it's quite interesting, right? Because 2S, 2R, they are in that. So these are mirrors. These stereocenters are R or S, okay? But the 3 is totally different. And it's the same, okay? S and S. So they are not enantiomer, right? Because 2S, 3S enantiomer should be 2R, 3R, okay? So here we have a new concept called diastereomer. So the definition of diastereomer is that the stereoisomer that are not mirror images, okay? We have enantiomer, we have diastereomer. All right. So, so if we summarize all these 4 stereoisomers relationship in this chart, so now you can see it in a more clear way, and you see we have 2R, 3R. Its enantiomer is 2S, 3S. Only one enantiomer. Okay. And then its diastereomer is if we keep 2R here, but flip this 3 position, 3S. If we keep the 3R position, 3R, and we flip the 2 position stereocenters, 2S. So these are 2 diastereomers, okay? So for each one of these 4 stereoisomers listed here, it has only 1 enantiomer, but 2 diastereomers, okay? Keep that in mind. And so we just talked about that enantiomers have the same physical property except optical activity. Okay, then for the diastereomer, they have totally different properties. Okay, so if we look at these 3 compounds properties here, so we have a 2S, 3R, and a 2R, 3S. So these are enantiomers, right? So enantiomers, they have the same physical properties, same melting point, same pKa, and they have exactly opposite specific rotation because it's optical activities. So that's the only physical properties that enantiomers are different in. Okay, then so 2S, 3S is it's not enantiomer to these 2, right? So 2S, 3S are both are diastereomers to both of these 2. Okay, 2S, 2S, but the 3 flipped, and the 3S, 3S, but the 2 position flipped. Okay, and you can see it has a totally different, almost every properties than the enantiomer. You can see the melting point is much higher, the pKa is a little bit lower, and the specific rotation of the optical activity, it has nothing to do with these two numbers. Okay, so if two compounds are diastereomers, they have totally different properties. Okay, so for diastereomers, this is a particularly important concept for compound with a lot of stereocenters. Okay, so here so if n equals the number of stereocenters in the molecule, 2 to the order of n is the maximum numbers of stereoisomers possible. So you need to keep this in mind. For example, so if we have a chiral compound or stereocenter with only one stereocenter, then 2 to the order of 1 should be 2, right? So if a molecule has a single stereocenters, it has 2 stereoisomers, which is the enantiomers, right? And then just as we talked about for these compounds, you have 2 stereocenters here. 2 and 3 position are both stereocenters. Then in theoretical view, that it has the possible stereoisomer number should be 2 to the order of 2, which is 4. And these are the 4 listed here. Okay, things become more complicated when the number increases. All right, so if we have, like in this case, 4 stereocenters, those 6 carbon sugars, then in principle we should have 16 isomers, right? Because 2 to the order of 4 is 16. Okay, so C6 sugars, 40 stereocenters, so 16 isomers. So, and it is very interesting. The natural world only provide 8 of these sugar isomers, which is listed here. For example, D-glucose, D-mannose, and the D-glucose. Okay, so 8 natural ones are shown here. And after class, you may spend some time trying to assign all these stereocenters. For example, each of them has 4 stereocenters, right? So can you assign the specification R or S of this carbon, or this carbon, or this carbon? So it's kind of if you are not quite familiar with this, it's a kind of a big workload because you have to assign 4 times. It's 32. It's 32 very good practice for you to apply the CIP rule and get familiar with the concept of ROS specification. All right, so don't miss this opportunity. Okay, and but not all molecules with 2 stereocenters have 4 stereoisomers. Okay, I know things get a little complicated for you here, but just after class, spend more time on this. But I will show you why. All right. So, for example, if we have a different compound with 2 stereocenters, like here, it's tartaric acid. Okay, so this is what we learned. 2R, 3R, it's enantiomer, 2S, 3S, right? And then another pair, 2R, 3S, its enantiomer should be 2S, 3R, correct? And then they have a mirror image here. Okay, the complicated thing is that for the molecule with 2R, 3S, it has an internal plane of symmetry inside the molecule already. Okay, so if you put a mirror here, the OH matches OH, COOH matches COOH, H matches H. Okay, it already has an internal plane of symmetry. Okay, so let's go. Let's remember the first thing we learned in chapter 4. If a molecule has an internal plane of symmetry, what does that mean? It's achiral. Okay, so although it has a single stereocenters like 2R, we can assign it because 2R is a stereocenter with 4 different substituents. Okay, it can be assigned R. The center is chiral, but the overall molecule isn't. Okay, because it has an internal plane of symmetry. So in this case, 2R and 3S, 2R, 3S, and the 2S, 3R, because they are not chiral at all, they should be the same molecule, right? Okay, so to make it clear, so we have 2R, 3S, 2S, 3R. Okay, this is the internal plane of symmetry. This is the mirror between them. Okay, so so I just told you, if you rotate the Fisher projection 180 degrees, it's the same molecule. Okay, if we rotate this to 180 degrees here, okay, they are the same molecule. If we would do nothing with this, just move it here, but this one will rotate 180 degrees, still the same molecule as this one, and now it's the same molecule with the left one. So that again shows that if there is an internal plane of symmetry, although you have stereocenters that can be assigned R or S, okay, it's achiral, so they are the same. So in this case, tartaric acid only has 2+1 isomers. So 2 of them are the enantiomers of 2R3R, 2S3S. Okay, so these two enantiomers are each other. See, and these two diastereomers are 2R3S, 2S3R. But unfortunately, 2R3S, 2S3R, they have internal plane symmetry. They are the same molecule and same achiral molecule. And for 2S3S also. Okay, so in total, tartaric acid also only has 2+1, 3 isomers, not 2 to the order of 2, which is 4 isomers. Okay, so all these complicated situation is because that there is an internal symmetry plane within the molecule of tartaric acid of 2R3S, 2S3R, and that makes them achiral, thus the same molecule. Okay. It's a little bit complicated, so be sure to practice and spend some time on reading of the textbook and the slide. Try to understand. Okay. And also, what we called this molecule, which has stereocenters but also plane of symmetry, is we called it a meso compound. Okay, this is the new name here. Meso compound is achiral but has stereocenters. Okay, just keep that in mind. And because meso compounds are diastereomers, just as we listed here, okay, meso compound is diastereomers with these two, okay, so they have totally different properties. We just learned that diastereomers have different properties, okay. So for the tartaric acid 2R3R, again, the only properties that is different is the optical activity listed here. All the other properties like density, solubility, and the melting point, they are the same. For the meso, because it is diastereomers as these two, so it has totally different physical properties. The melting point is much lower, and the density is much lower, and the solubility is much lower. Okay, and then, just as I told you, meso compounds are achiral, so it doesn't have optical activities. All right, keep that in mind. Okay. Here are some list. It's a list of some other meso compounds. For example, if you have so if I ask you to quickly name this compound, you can, right? Because you have learned the nomenclature by yourselves. Okay, I assume that. So this is a 1,2-dimethyl cyclobutane, right? And if you name it fully, it should be cis 1,2-dimethyl cyclobutane. Okay, so it has stereocenters. For this carbon has a methyl, and the two alkyl are different because of this methyl, and another one is a hydrogen, right? It has two stereocenters, but it also has an internal plane of symmetry, which is here, as I showed here. Okay, then it is meso. Okay, and for this one, it's more complicated if you want to name it. But let's see, is this the stereocenters? It is, right? Because it has a methyl, it has a hydrogen not shown here. It has one side of the ring structure that has a chloride, and another side of the ring structure which has an alkene. So 4 groups are different. So this is a stereocenter, and this is also a stereocenter, right? So it has stereocenters in this molecule, but it also has an internal plane of symmetry drafted here. Okay, so this is also a meso compound. All right, for those who are really interested in this topic, actually, several weeks ago in our research, so we actually encountered this problem during our research. So one of my postgraduate students actually wants to do this reaction. So she wants to reduce both of the ketones in this molecule. So if you look at the starting material, is it chiral? Is this the stereocenters? No, right? Because this center has 2 of the same functional group, which is the ketone and the ketone here. Okay, this molecule is totally achiral molecule. Okay, and then if you reduce both of them, now you have an OH here and OH here, right? So is this a stereocenter now? It is, right? Has a methyl, a big alkyl, and OH, and an NH, right? So is this a stereocenter? It is, right? So it has stereocenters now, okay? But does it have a, so the ROS of these two stereocenters actually determines the overall chirality of this molecule, okay? So if you are interested after the class, so you just try to figure out how many stereoisomers are there for this compound. And what's the relationship between all these stereoisomers if you figure out all these ones and you try to match them. Oh, these two are enantiomers and these two are diastereomers, and is there any meso compound? So this is kind of quite difficult. So that's beyond the requirements for this course, of course. But just for some of you that are interested in this topic. Okay, then we already know the concept of meso compounds, right? Then I'm going to introduce you another concept called the racemic mixture. Okay, and it's not something that is so a racemic mixture is more like a physical concept, something like that, because you mix the two pure molecules together. So a racemic mixture is a 50% mixture of two enantiomers. Okay, you have 2R, 3R, 2S, 3S. So they are enantiomer. You can draw a mirror here, and then but if you mix them together, so that's called a racemic mixture, and you have a meso, which has the internal plane of symmetry. Okay, but two stereocenters. Okay, so the thing you want to remember that a racemic mixture is not optically active because the equal and opposite rotation cancel each other out. So if you put a polarized light through this cell, and 50% of the content of your mixture will rotate the light to one direction. Okay, and another 50% of your mixture will rotate the light to the opposite direction. So the overall effect that for the observer, that is you, is that you didn't observe any rotation. Okay, but it is not because the molecule is chiral. It is because it's a mixture of two enantiomers. Okay, but for the meso compound is not optically chiral because it is achiral, because it has the internal plane of symmetry. Okay, the molecule cannot rotate the light at all. So each of these molecules can rotate the light, but if you put the equal amount of them, they cancel each out. They cancel each other. Okay, so that's the concept you need to be clear. All right, so let's talk about how to so for a racemic mixture, just like Louis Pasteur discovered for the parallel tartaric acid, it turned out to be a racemic mixture because it's 50% plus tartaric acid and 50% minus tartaric acid. Okay, so if you have a racemic mixture in real life, how do you separate them? If you just want one of the enantiomer, you want the chiral part, you want a chiral molecule, but they are mixed together in equal amount. How do you do that? So several hundred years ago, Louis Pasteur did that, right? What did he do? So he did salt formation and the recrystallization. Okay, so you know that now you know that it is proven for hundreds of years that recrystallization itself can separate a racemic mixture. So you have a racemic mixture of this, and you can separate to get a pure plus tartaric acid and the pure minus tartaric acid just by separating these two crystals. Okay, so but not all compounds are solid, right? So what if you have a liquid racemic examples, you basically cannot make it solid. And how do you do that? So we have chemical ways to do that, okay? So now we goes back to the concept of a chiral-chiral interaction and chiral-achiral interaction, okay? So what we do to resolute or to separate the enantiomers is that we convert them to diastereomers, okay? The concept, the essence of this concept is that enantiomers usually have the same physical properties, right? That makes it very hard to isolate, to separate. But diastereomers, as we just learned minutes ago, they are different in many properties, okay? So they can be separated, okay? So, but if we have a chiral, which is here, and chiral-achiral interaction, like the hotel slippers, you have your chiral right feet, your right foot, you have a chiral left foot, you wear into a slipper that is achiral. both of your feet feel comfortable, right? So you cannot, so there is no energy difference. Both of feet are very comfortable with the achiral slipper, okay? So in the chemical way, if you react with RS mixture with an achiral base, in this case, acid, base, they react to form salt, right? But these salts, they are equal in energy because they are, again, mirror image with each other because you introduce an achiral element, okay? So they are mirror images. They are still enantiomers, okay? If you can't isolate these two, how can you isolate these two enantiomers, right? So if you react a mixture, a racemic mixture with achiral reagent, the products are enantiomers and you cannot separate them. Okay, then we have a different situation here. What if you use a chiral amine? Okay, in this case, that refers to your sneakers, right? So you have your right foot, your left foot, and here you have your right sneakers, your right shoe, okay? Then it will interact differently, right? Because your right foot will be very comfortable in your right sneakers, and your left foot, they are totally uncomfortable with this right shoe, okay? So in this case, sometimes we can use some kinetic way to isolate it. So for example, your right foot is more, your right foot is more likely to wear the right shoe, okay? But what if we use excess amount of these chiral amine? So if we react both of them, so in this case, you have a RR salt, which is RR here, right? At the bottom, you have SR salt, which is the R amine reacts with S acid. Okay, now are they enantiomers still? No, right? Because you now have RR and SR, they are diastereomers with each other. So that means, although you cannot separate a racemic mixture of enantiomers, you can use a chiral reagent to react them into different diastereomers. And because diastereomers now have different properties, then you can isolate them. Okay? That means resolution can separate enantiomers due to the different properties of diastereomeric products, which is listed here like this. Okay? So as I said, a chiral interaction or chiral interaction, it can be also used in other way. So the question is that, can we separate enantiomers not based on the diastereomeric product, but because of different reaction rate or different properties of the starting enantiomers? Okay. What if we use a chiral reactant that reacts with our enantiomers really quick, but the rate between the chiral reagent and the S enantiomer is really low. Okay, for example, if we have a chiral reagent that can react with the R enantiomer, the rate is 100 faster than S. Okay, so after 101 reactions with this reagent, we have a mixture with 100 of this and 1 of this. Then that's also a good separation, right? Okay, so if you are interested, you can read the Wikipedia page of the kinetic resolution, which is a resolution based on the different reaction rate of the starting enantiomers. But for this course and the exam, there's only the resolution based on the property of diastereomeric products, like listed here, example listed here, is required. Okay, the Wikipedia thing is just for interest. All right, so we have 5 minutes left. So let's just go through a little bit very quick review of the isomerism. All right. So for the isomers we have learned, and you have learned previously, so we have a constitutional isomers and the stereo isomers. For the stereo isomers, we just learned in chapter 4, there are enantiomers, which are mirror image, and the diastereomers, we are non-mirror image, that is, have totally different physical properties and the chemical properties. And then for the diastereomer, we have a cis-trans diastereomers based on that. If you have a ring structures, you have different faces: bottom face, top face, and if both, we'll talk about this. And also configurational diastereomers, which is like RSSR. Okay, so this is constitutional isomer. For example, if you have the C4H9, same formula, right? So different carbon skeleton, constitutional isomers. And different functional group, constitutional isomers, okay? And the different positional functional groups, primary amine, secondary amine, both same formula, constitutional isomers. Stereoisomers with the same bond connections, okay, but different spatial rearrangement. So enantiomers, you already learned mirror image. That's the right, RRSS plus minus, okay. And then we have diastereomers, that molecules with the same bond connection but different spatial arrangement that are not related as mirror image. For example, 2s, 3s. Its mirror image should be 2r, 3r, right? But it's not mirror image, so 2r, 3s. So you can say these two diastereomers. And as I show you in the summary there, cis trans is also a diastereomers.